So here we are in section 5.2, where we are talking about the log rule for integration. That's really where, we want to be over here. And this is something you might have learned in Calc 1. Sometimes they don't get to this, or it's not in the curriculum. So this is potentially new. Right, 1 over x dx, we have this antiderivative rule of natural log absolute value of x. And if you can, make those absolute value symbols obnoxiously clear, right? Like take a Sharpie or something and make sure that you have absolute value symbols around that x. Now, as soon as we learn, an integration rule, of course, they're going to work in the chain part to it. They're going to work in that u substitution. This will work also, this technique, if you use a u substitution and you end up with 1 over u du, well then its antiderivative is the natural log of the absolute value of u plus that constant of integration. So I want to just address, why do I have absolute values here in that antiderivative? It just comes up. It's a common question, like, why am I doing that? So let's go back over here to the derivatives. Remember when we talked about the derivatives of natural log? We had this extra disclaimer here, like, hey, the derivative of the natural log of x is 1 over x, but watch out, it's really only defined where x is greater than 0. And that is because if I actually draw the natural log function on this graph, it goes through 0, 1, 1, 0 there, and it looks like this. What we were saying is it made no sense to have this other piece of the graph. Like I have to kind of rule this out, because if your original function is only defined from 0, let's put that domain, from 0 to infinity, then our derivative should only be defined from 0 to infinity. So that's why we lopped off half of that graph of 1 over x, right? But if I am now thinking about integrating 1 over x, well then I have to cut all of this out. I'm gonna kind of cut what I just did there. Because now when I think about this, like this is the graph of 1 over x. Well, I have it down here labeled, right? This is defined, well, the domain of this is, let's write it. The domain of this function is negative infinity to 0, union 0 to infinity. I need an antiderivative that actually is defined on both of those intervals, right? So that's why we have this absolute value on the natural log, because what that ends up doing is it allows negative numbers in that logarithm that was never usually allowed. Evaluating the natural log of -2 is undefined. Try it in a calculator, you don't get an answer. But if you put absolute value around it, well now it's possible. The natural log of absolute value of -2 is the natural log of 2, and that's a number. That's possible. So it ends up like just kind of mirroring on both sides. So this is really your antiderivative for 1 over x. Okay. Now again, there is a vertical asymptote here at x equals 0. So 0 is not within the domain here, but that's kind of implied from that antiderivative rule. So I just wanted to address, why do we have absolute value in there? And that's just a little graphical interpretation of why that's needed. So when we get into our practice problems here, we're just going to kind of work on those log rules for integration. We're really kind of focusing on these, and it's not a terrible antiderivative rule to remember. I'm going to fly to our practice problems here. This is pretty much on point as far as what that rule is. I just have that sneaky 2 down there, and I can handle that pretty quickly because I can just take that out as a 1/2. It's just a coefficient, so that's legal. And now you can say, well, I have the integral of 1 over x dx, so I'm just going to kind of carry along that 1/2 for the ride, but make sure that you actually have absolute value on that x variable. It's really important that it's there, especially when we get to definite integrals and evaluations. It needs to be there. So that's a pretty basic one. If I move on to question number 2, a lot of people will just do this one in their head. which is fine. But I would prefer it if you viewed it as saying, look, I don't just have x in the denominator, I have this x plus 2. You can't separate terms of a denominator algebraically. That is terrifying. We can't do that. But what I can do is say, let me just make that whole thing be equal to u. Let's handle this as a u substitution. It's a pretty nice one because it's pretty standard. If I take the derivative of both sides, I mean du equals dx, there's no even weird issue going on with coefficients. And then I'll switch back that integral. So again, I have this integral. It was 1 over, and then I let that entire denominator be u. And then I'm just simply replacing dx with du because I'm allowed to, because my work tells me I can do that. And then I can go with my antiderivative here, which is natural log absolute value of u plus c. And then I will convert back to the x variable because we should definitely do that all the time. So just make sure that those absolute value symbols actually look like absolute value. You can make them obnoxious if you want to. Make sure they're not like kind of curvy because I will read that as curvy, and that's a problem. Okay. So now we have this almost like this new technique for u substitution. Not only can you use u on something that's inside, like the inside part of a composite function, now you can kind of use it and say, well, let's just make the whole denominator u, and let's see if we can get that to turn out. And when you say that, like, hey, that's a good strategy, you're trying to use this rule of like 1 over u du has a known antiderivative. So I'm going to use that strategy over here in example 3 because, again, you have no algebra tricks up your sleeve. You can't separate a denominator here, but I can say, let's let that be u. Let's see if that's going to work. Let's do the follow through because, it just happens. It just falls out of it. And let's solve for dx. Right? That's a similar u substitution that we had in the last video. The integral is different. So I'm going to switch this over and say, okay, what did I just do? I have an integral with x over something. Let me put that something in there. I let that whole denominator be u. And now in place of dx, I'm going to write du over 8x. And this is mission accomplished because I see those x's there, but I also see that they completely cancel each other. You have one in the numerator, one in the denominator. They are gone. And so I'm left with this integral. 1 over u du. I'm just going to handle that 8 there and say that's just a coefficient out in front. So now I can come up with my antiderivative, which I can then rewrite back in terms of the x variable that I was presented with. So again, make those absolute value symbols as obnoxious as possible. It's really important that you do that. Okay. Now, I'll just mention this whenever I can. If you feel uncomfortable about this being the right answer, you have a way of handling that. You could take the derivative of this answer and end up with the original thing inside. And if you do that, it will check out, but it should make you feel better about checking your work. You have a way to do that. Okay, now I'm going to do the same thing on problem 4. This is equally frustrating, right? Because you have that denominator. You can't do anything to separate that denominator. And again, there is no quotient rule for integrals. But I can use this now as like a new strategy. Like, let's try this. Let's let u be the entire denominator. And let's work on that follow through. And let's get a good replacement for what dx will be. So you're kind of replacing u and the dx. So you're kind of putting both of those in. So I'm going to take a look at this integral now. You have e to the x. That whole denominator is what you let u equal. That's what I'm after. And then in place of dx, that's got to go too. I write du over e to the x. So this is great because those e to the x's are gone. You have to get rid of any remnant of an x variable that was ever in your original expression in order for u substitution to be deemed successful. And this is awesomely successful with a known antiderivative. And then I will switch back to the x variable. Now, I'm going to be honest with you here. This is great. When you check your work or, I don't know, you're kind of taking a look at the answers here, it is legal for you to relax the absolute value symbols on this particular antiderivative, this particular answer. I could not relax the absolute value on any of the previous examples that we had done. The reason I'm permitted to relax them and straight up change them from these obnoxious absolute value to the curvies is because this expression inside here is never actually negative. Remember, e to the x is positive values everywhere. When you add 1 to it, it's still positive. So either of these are great. But if you're worried about it, then always use the absolute value. But you will see them relax the absolute value from time to time. And that's only going to happen, again, where that inside piece is always positive. I cannot relax it here. Just think about it. If you let x equal 0, now you have -7 under there. So do not relax the absolute value. We need them desperately on that antiderivative. Okay. So we've got a couple of things going on in this section, and some of this might have been covered in a Calc 1, some of it not. So we're gonna get in here and do some of these. Okay. So here I have example 5, where I'm just going to kind of keep working on this new idea, this new strategy, where, like, again, I can't do anything to break apart that denominator, but I can try to do a U substitution technique. So all of these Calc 1 skills are on the table. They're certainly important, and I need to make sure that you're okay with them. We're now sort of applying U substitution in this new way with this new integration rule. So once I set the U, I always do the follow through, and then I just algebraically solve for dx, because I'm going to have to get rid of that guy too. I'm doing both things. I'm replacing 1 minus 4x for u. I'm also replacing the dx. And I would say this worked. You've gotten rid of all of your x variables. So this is considered something that works and is good. I'm not bothered by the fact that you have those extra coefficients flying around. You have achieved your goal of having something that is now able to come up with an antiderivative. It works great. The only thing I have to do is switch back to the x variable. And again, this is one of those problems where you desperately need the absolute value symbols in here, because you can clearly see that, letting x be 0 or letting x be 1, you'd have negative numbers in here. So don't relax the absolute value unless you're absolutely sure that you can. Okay. When you see something like question number 6, this is different. You have 2 terms in the numerator and 1 term in the denominator. So we kind of handled a situation like this on that integral refresher in the last video. You can handle this, and you can do it algebraically like we did on the last video, or you can do what's known as like short division. This is legal for you to say, you know what, I don't have to have x plus 4 all over this common denominator of x squared. What I can do is just kind of get in here and say, well, I can have x over x squared, and I got 4 over x squared. You're sort of unpacking that common denominator. This is legal. This is absolutely appropriate for you to do this. And you're just changing the way that it looks. Most of your math life has been spent with math teachers saying, hey, get that as a common denominator and simplify your work. And here I'm asking you to go in the opposite direction of like, let's decompose this and break it down. And so you're doing this so that it's easier to come up with an antiderivative, because you could integrate term by term. And so while this takes one expression and breaks it into 2, I can definitely clean up each one of those and have things that are really nice to work on for integral work, right? And so you have a combination of things here. I know the antiderivative of 1 over x is natural log absolute value of x, so I'm gonna write that, natural log absolute value of x. And I know here what you got going on there is the power rule. You got 4 times x to the negative 2. Notice I just brought that up with a negative exponent. I'm going to add 1 to the exponent, divide by my new exponent, and slap a plus c on it. So I'd like to regroup a little bit. And there is my good-looking antiderivative. Okay, so this is what's known as like a short division. Just like break something up. If you have a bunch of terms in the numerator and a monomial in the denominator, you can handle that pretty effectively. Okay. If I move on to question number 7, if I reverse, what's going on here? If I sort of go back to this idea of having, 2 terms in the denominator, well, then I have to be careful. You cannot break up. When I keep circling this and saying, like, you can't break those up, this is not a short division situation. You have 2 terms in that denominator. You can't break those up. Okay, this is your denominator. This is one fraction. What I can do is go back to the strategy of saying, let's let u equal x squared plus 4. Let's see if that works for me. It's a really effective strategy that you're going to use in the future. So again, once I do that follow through, I just solve for dx, because I'm going to need it. I'm going to need to get rid of that too. I need to get rid of everything with an x. My hope is this x over here will go away. That's what I'm always trying for, right? So I take the integral. I've got the x. I'm crossing my fingers that will go away. And for those of you that see it, you see it. That denominator is u. In place of dx is du over 2x. So mission accomplished. You have successfully gotten rid of that x variable that you were hoping would disappear somehow, and it did legally disappear. And so what do I have? I have that 2, which is really a 1/2 coefficient, and once again you're on to that 1 over u du. Okay, this would be one of those problems in this particular case where if you wanted to relax the absolute value symbols, you could. You do not have to. If you just want to make sure you're right all the time, then go ahead and put them in. But you will definitely see the final answer in textbooks be relaxed. Okay, so I just want to discuss it. I don't want to think I'm doing something different. I'm just saying, look, this x squared plus 4 is always going to be positive. Whether you let x be 0 or negative 5, once you're squaring that, it's always going to take on a positive value, so it's okay. All right. Now, if you can kind of see I'm just playing around with these x squared, x, and 4. If you take a look at 8, it's the complete reversal, top and bottom, of what question number 6 had. I just reversed them, right? This totally changes the problem. This is no longer, what did I say? I said, a lot of people call this a short division, because it's just a monomial down there. And so you can handle that pretty quickly using algebra. But number 8 is not. And so the opposite of a short division would be a long division. So maybe that's why I use that term, right? This is long division. Why do I want to do long division? This is what's known as an improper fraction. You know that just from, middle school, right? When you first learned, let me slide this over so you can see it. When you first learned about simplifying fractions, if you have 10/3, that's improper. Let's switch it to a mixed number. It's pretty much the same idea. Let me just kind of show that example, right? That would be, what would that be? 3 1/3. You kind of rewrite it. It's improper because the number in the numerator is larger than the number in the denominator, right? It's top heavy. You've got to knock it down. Let's tone that down and rewrite it, right? So we kind of wrote it as a mixed number. That was many years ago for a lot of you. But this is the same issue. You have something here that is improper. The degree of the numerator is larger than the degree of the denominator. I don't even see it. I have to put a 1 in there. So an improper fraction, let me just cut this part out. My old middle school example here. An improper fraction happens when the degree of the numerator is greater than or equal to the degree of the denominator. Okay, so let's just kind of slide left here, right? See how example 7 was proper. This degree was a 1 and the denominator was a 2, and so that's an appropriate fraction. I was able to integrate that just by using my new trick of letting u be the whole denominator, and I worked out. But number 8 is improper. You have to do a little bit of work, and you need to simplify first. So let's use that word. You have to simplify the expression the same way that you would simplify numbers back in middle school. So simplifying basically means use a long division to simplify this. So we'll do it. I'm going to get into some heavy-duty pre-calculus here, or fancy advanced algebra technique. What do we do? When you have something like a number, I'm just going to keep using that example, right? Like that 10/3. How you do it is you would put 3 and then you put 10 inside, right? And I'm going to do the same thing here. What am I going to do? I'm going to put the x plus 4 on the outside and x squared inside. Now, with polynomials, it's usually a good idea if you don't have some terms that you put zeros in there. So you just put it in standard form and work your way down. And so going back to my number example, you say like, how many 3's fit inside 10? Well, I'm not really going to do that here. What I'm going to do is with the polynomials is I try to match the first term exactly. I'm going to multiply x by something to get exactly x squared. And so what's going to do that is multiplying by an x. I'm going to distribute that x to both of these guys. And then here comes the critical moment here of at this moment you're subtracting that expression. So the reason you wanted to match that first term exactly is so that those x squareds get annihilated. X squared minus x squared, that whole term is eliminated. That was the whole point of matching it. But what I have here is I have 0x, right? I didn't have anything, minus 4x. So what that means is your remainder that you're pulling through is a negative 4x. Now I'm going to bring down the next term, which seems pretty silly because it's a 0, but I'm going to break down the next term of my division, and I'm going to play the same game again. I'm going to say, look, I have this thing. Let me choose a color. I have this thing, this x, and I want to multiply it by something to get exactly negative 4x. You want to match it perfectly, so that means you want a minus 4 up here. And you're going to do the same thing. You're going to distribute. And then you're going to come at this with that really interesting moment of like, hey, you subtract all that stuff. And this is the point. Negative 4x minus negative 4x, that's positive, right? These get annihilated. That's the whole point. But then 0 minus negative 16 is actually 16. That's your remainder. So what does all this mean, right? I just did all this like heavy-duty algebraic manipulation, work, simplification, whatever you want to call it. What I'm going to say is, look, this was my original integral. It was improper. I'm going to rewrite it down here so that we can see it. What I have just done is I have simplified it. I have equivalently decided that when you divide these things, what do you get? Well, you get x minus 4, freestanding, and then you have that little remainder. So you put the remainder over what you were dividing by. This is an equivalent statement. This is an equals sign, 100%. And I didn't have a way of addressing that original question, that original integral. It was top heavy. I have to simplify first, but now all my focus is over here. I'm like, okay, well, what do I do with this then? Well, you have things really separated out term by term. You can handle each term separately, and it's great. And you can kind of just work on it, right? Like the integral of x is 1/2 x squared. Done. Move on to the next term. The integral of negative 4 is negative 4x. I'll do a little bit of side work here. Maybe that's not the best color. Here we go. This is another u substitution in here. You're kind of letting, the entire denominator be u, and you're trying to work this out. This is really the integral of 16 over u du, which fits into the notes for today, because that's really the natural log of the absolute value of u. I know I have a 16 in there, but that's okay. And let me put all of this together, right? Let's go back to that color. Oop, nope, not as a highlighter. You have 1/2 x squared minus 4x plus 16 times the natural log, absolute value, x plus 4, and don't forget about your constant of integration. There is your antiderivative. Okay. And I'm actually okay if you kind of like do this part in your head. A lot of people would just kind of solve that, but definitely make sure this is not one of those times to relax the absolute value. It must be in play. All right, so that's a little bit of like algebra, heavy algebra here. You know, the difference between a long division problem, like number 8, it was, you know, bigger power in the numerator. And notice it's improper if the degree of the numerator is larger or equal to. I just want to point that out. And question number 6 was a short division where it was a proper fraction. You had a higher power in the denominator. So just a little bit of algebraic prowess there to get us through these problems. So let's handle the last couple here. Number 9 certainly tends to terrify people, but we are talking about the integral of 1 over x dx being natural log absolute value of x. Where does this come into play? I'm definitely not going to let u equal x. You almost never do a u substitution, by saying like, oh, let u equal x. That almost never happens because nothing amazing happens here, right? Like, what do I get? I get natural log of x over u du. This is a serious problem. You have a function of x still left over. So generally, we don't ever make a swap of u equaling x in a basic u substitution. That's not really going to work. But what I want to point out here is you know the derivative of the natural log very well, and let's just capitalize on that. I'm gonna make the argument that if your integral involves a natural log, I'm actually going to let that be the u substitution. I know that that's kind of like a little detour that I've been saying. Usually a u substitution is something inside something. It's composite. In this case, I'm going to let u equal the entire natural log function. It's not composite. It's just kind of hanging out there in the numerator. But I'm going to try to see if I can get this thing to work, meaning can I successfully switch this integral over into the u variable and have no more remnants of an x variable left over? So let's just try it. I'm going to take the derivative of both sides, and I'm going to make this say dx, because I got to get rid of the dx too. So that would be, oops, let's undo that. Whatever happened there. I'm going to multiply the x through, and that will give me an equivalent statement for dx. So what am I doing? I'm changing my integral. I still kind of have that x kind of hanging out over there, but I let the entire numerator, which is weird, because the numerator was natural log, I'm just letting u equal the natural log of x. I'm going to also replace the dx. And this straight up works. This is legal. Everything is great. You have successfully gotten rid of those x variables. And so what am I left with? I'm left with something really manageable. I'm left with u to the first power. This is power rule. I have an antiderivative for that. You bet. Mission accomplished here. I mean, I'm not done yet because, my integral was in terms of x, so my answer should be in terms of x. And don't be weirded out. U was the natural log, so make sure that that goes in parentheses. Watch your handwriting here. Okay. Don't write something like this, because that has the tendency to imply that you're squaring the x variable, right? So make sure you get in there and put those parentheses around it to make it great. Okay. Okay. All right. So here we have another example. This is our last guy, and just I felt you probably need another problem to practice this. This is technically an improper fraction. We are not going to do anything crazy and silly like, oh, I can cancel those x squareds. No, you can't, because this whole term is in the numerator and this whole term is in the denominator. using our strategy of saying like, oh, I'll just do a u substitution. Let's just let u equal the whole denominator like we've done in some of those past examples, which I have to do correctly. This is not going to work for us, right? Because what would I have? Well, I have this integral that has this x squared plus x plus 1. Pretty complicated numerator. I did let the whole entire denominator be u. That's great. And then in place of dx, I could write du over 2x. But this is not awesome. You can't cancel anything, by the way, because this is all stuck together. You can't even cancel like the x in there. Nothing is great here. So you tried a u substitution. You tried a really great strategy that we have talked about in this lesson a lot. Like, oh, let u be the whole denominator. It just doesn't work out all the time. It doesn't mean that this was silly or stupid to try. It just means it didn't work. So no problem. I want you to look at it from the light of like, hey, this is, I wonder if I can cut that. Cut. This is improper. Remember that we talked about improper. An improper fraction is when the degree of the numerator is larger than or equal to the degree of the denominator. And that is definitely happening here. So what I can do to address this problem is simplify this improper fraction, and I'm going to simplify this improper fraction with a long division. Now remember, what you're dividing by goes on the outside. I'm going to put a 0x there, just as a placeholder, and the numerator goes inside. And I like to space it out and see what happens. Okay. So what I'm going to do to run through this long division again, because it's been a while for a lot of you, you want to multiply x squared by something to get exactly x squared. Well, it's just a 1. You don't need to do anything fancy. I'm just going to put a 1 up here. And once I decided that, that 1 kind of distributes to each one of those puzzle pieces, right? So I get x squared, I get 0x, I get a plus 1, and here comes the tough part of long division. It's this like subtraction step. The whole reason you wanted to match that first term is so that you annihilate the first expression there. X squared minus x squared, because they're perfectly the same, they are gone. That's the whole point. Now, when I take a look at the next one, x minus 0x is x. That's it. And then 1 minus 1 is actually 0. So this is your remainder. That's my remainder. My remainder is x. So let's transform this integral. So certainly this is the integral that we had when we started. And what I'm going to say is this is equivalent to, well, 1 plus the remainder over what we were dividing by. This is a legal algebraic equivalent expression. It took a little bit of long division in there to make it work, but now that I have an equivalent integral, I now have them separated by this plus sign. I can handle each one separately, and I don't know, the integral of 1 is just x, like done. I don't need anything crazy. When it comes over here, I'm going to use that new kind of strategy of saying like, well, this is a proper fraction. I see the degree of the numerator is smaller than the denominator. And I'm going to use that strategy of saying, let's try letting u be that entire denominator. Let me work on that follow through and see what happens. And so this is successful, a successful u substitution, because you managed to get rid of the x variable, and you're left with something doable here, that the known antiderivative is the natural log of the absolute value of u. I don't want to forget about this other term that's part of my antiderivative, right? And you can see how awkward this looks, because you have an x variable and a u variable. We have to convert this over. And so there is a good-looking antiderivative. Once again, you will see textbooks and other authors and things like that. They will relax the absolute value on this because it's possible. Because that expression inside the logarithm is non-negative, you can relax and sort of eliminate the absolute value symbols here.